Hi guys, I welcome you to my YouTube channel, and today I got some free time and decided to record another practical which has been done by my students. I'm trying to just give you a picture of how to attempt or how to produce your or to present your work in advanced practical skills. That is in AS Physics 9702, that is paper 3. So my students have done a paper which is May June 2009, and it is paper 3-1. You can download the paper, or if you already have it, if you're a teacher, you can just print it and give it to your students. The apparatus are easy to find in the school. You don't need to purchase anything. So I just want to show you how my students produced their work, how their work was laid out. So let's go. So without wasting time, this is the paper. It is it's May June 2009. It is paper 3-1, and we are still doing question number 2, advanced practical skills question number 2. So let me take you to question number 2 without wasting time. I'll record other videos for question number 1, but basically question number 2 is where people get a lot of challenges. Okay, so this is question number 2. In this experiment, we will investigate the angle of tilt of a bottle when it contains different amounts of water. Use the water supply to measure the volume of the bottle. Of course, if you're a teacher and you check through the confidential, that you were asked to provide students with a measuring cylinder or a pipette. So students are going to measure volume. My students measured volume using a measuring cylinder, and the measuring cylinder they used had accuracy of about it had a precision of 1 centimeter cubed. It would read up to 1 centimeter cubed, or the smallest value it could read is 1.1 centimeter cubed. So uh, the water bottles I used are these water bottles of around which have around 500 milliliters. So my students got, because they filled the bottles to the top, this particular student whose results I'm using to record this video got 501. So she recorded 541. So she recorded 541 centimeters cubed. So just pouring the water from the bottle to the measuring cylinder, or actually my students were emptying the bottle into the measuring cylinder as they record. Because the measuring cylinder had a maximum of 100 milliliters, so they had to do this to empty the bottle almost five plus times. So they went on adding to note the volume of the measuring cylinder. And this particular student found the volume of the water which could fill the bottle to be 541 centimeters cubed. Remember, I said I used bottles which are normally labeled 500 milliliters. So if normally when it is not full to the top, it is supposed to hold water 500 milliliters of water, but if you completely fill it to the top, there will be an extra small volume. That's why this student got 541 centimeters cubed. That one is easy to do. Pour the water, empty the bottle into a measuring cylinder as you add up. I'm interested in this part here. This is the only part which could bring challenges to students. Justify the number of significant figures you have given for the volume of the bottle. Why have I recorded the volume like this? In fact, I've recorded the volume to the nearest centimeters cubed simply because the measuring cylinder that I've used is precise to 1 centimeter cubed. So the volume is recorded to 3 centimeters cubed, to 3 significant figures, since the measuring cylinder. So the measuring cylinder that I used, the measuring cylinder used is precise to 1 centimeter cubed. So the precision of the measuring cylinder that we used was approximately 1 centimeter cubed. Therefore, it was easy for us to record the volume to 3 significant figures, actually to the nearest centimeters cubed. Add water to the empty bottle until it is about half full, so you can perform that experiment. Measure the height h. So if you're a student and you want to perform the experiment in school on your own, you can just ask the teacher to print for you the confidential instructions to know which apparatus is needed. And these apparatus, you can find them in school without necessarily purchasing them. You can just find them in school. So my students, they said the water bottle was about half full. So my students were measured this height here, and this particular student got a height of 8 centimeters when the bottle is half full. Remember, I used these small water bottles of about 500 milliliters. Because this was measured using a ruler, she recorded this to one decimal place. So this is 8.0 to one decimal place in centimeters. As simple as that. You may not, because they said about, it may not be exactly 8.0 when you do the experiment. It could be higher or even lower, but it's just about half full. The angle of tilt, theta of the bottle, is the angle it makes with the horizontal when it is about to topple, as shown. So making sure that the lid is secure, tilt the bottle as shown until it is about topple and measure theta. So this angle, measuring this angle theta, cannot easily be done once because the bottle, first of all, was not having a flat edge. This edge here was not flat as it appears in the diagram. So measuring this angle here was a little bit tasking, and it was a little bit hard. So students had to take the measurement twice. When you're measuring an angle by holding a protractor in your hands, most likely the best value is going to be the average. So every time I take a repeated value, I draw a neat table. So my student drew a neat table. Hope I didn't skip any question. No. So my student was able to draw a very neat table. So you don't need to draw so many columns because the examiner will be just marking the method or the fact that the student knew that he had to take repeated measurements. So you don't need to waste time doing so many attempts. So just 2 columns are enough. So my student measured this angle for the first attempt and she got 57. Of course, she was using a protractor which is measuring to 1 degree. So this the precision in the protractor was 1 degree, or the smallest value it could give is 1 degree. So these are, I expected these to be whole numbers. So the first attempt she got 57 degrees. She tried to do it the second time and she got 54 degrees. Of course, there is supposed to be a variation because you are holding the ruler and you are at the same time trying to check if the boat is about to topple. So the average value of theta is going to be 57 plus 54. Divide this by 2. So I'll check her values. 57 plus 54. Divide by 2. And she got, this is 55.5. Because I want to maintain the same degree of accuracy, so I encouraged my students to round off this to 56 degrees. So this is approximately 56 degrees. Then estimate the percentage uncertainty in theta. So for percentage uncertainty, if you just look at the protractor, this kind of measurement, the protractor has the least count or the smallest value, which we scientifically call the least count of 1 degree. That is the least count. But note that when you are holding it in your hands, the answer and taking a measurement with an edge which is not very flat, most likely you increase the absolute uncertainty increases. So every time you use a protractor, we expect an absolute uncertainty between 2 to 5 degrees. So method 1, you will tell the examiner that the absolute uncertainty in theta is any value in this range. So for example, I will take a value in that range, I may take 4 degrees as my absolute uncertainty. Then I would say percentage uncertainty in theta is going to be 4 degrees divided by the value of theta, which is 56 times 100. So this is giving me 4 divided by 56 times 100. So this is giving me 7.1%, 7.1%. That is one method. Alternatively, since I have repeated measurements which are different, then I can say absolute uncertainty is half of the range. So I'll use a different column. Alternatively, I will say the absolute uncertainty in theta is going to be half of the range. That is half of 57 minus 54, which gives me half of 57 minus, of course, 57 minus 54, that is 3, divided by 2, which is 1.5. So this is 1.5. That is absolute. Of course, the absolute is in degrees. So then the percentage uncertainty in the theta is going to be 1.5 divided by the true value of theta, which is 56 times 100. So when I press my calculator, 1.5 divided by 56 times 100, so I get 2 point, that is 2 point, approximately 2.7%. Now some student will ask, but teacher, the answers are not the same. They're not supposed to be the same because the methods are totally different. And this is an uncertainty, where in the first case we estimated that it could be approximately 4 degrees. The second case, we are using a method of half of the range. So the examiner will not mark at the answer. The examiner is interested in the method. And the method is either you have chosen an absolute uncertainty which makes sense, or you have calculated the absolute uncertainty from half of the range. So I'll just take one of the values. So I will say maybe it is 2.7%. It can also be 7.1%. Okay. Then measure the volume V of the water in the bottle. So when it is half filled, my students were just emptying the water into the measuring cylinder. And this particular student got the volume, half bottle. Remember, it was about half full, so it is not exactly half. And her volume was 231 centimeters cubed. Empty the water from the bottle, refill the bottle so that it is about a quarter full. So this was again repeating the experiment so that it is about a quarter full. And then repeating B Roman 1, B Roman 2, B Roman 4. What is B Roman 1? B Roman 1 was finding H. So remember, it is a quarter full. So my student measured H and found H as 5.2 in centimeters. Then for theta, she carried out this again 2 times. So she had to draw a table. So let this be theta 1 in degrees. Then the second attempt in degrees. So the first attempt, remember we are repeating B, which involves tilting until it is just about to topple, to then measure theta when it is just about to topple. Of course, when the liquid is reduced, the angle of tilt becomes smaller, the angle of toppling becomes smaller. You can try that in your lab and see. So my students' measurements included 40 for the first attempt and 42 for the second attempt. You may not get the same answers when you are carrying out the experiment. So this student has her value of theta as 40 plus 42 divided by 2, which is 41 degrees. So this student has her value of theta as 41 degrees. Then she measured the volume. Of course, to remember, it was a quarter full. It was about a quarter full. Not exactly a quarter, but about a quarter full. So She measured the volume by emptying the water into the measuring cylinder, and she got to 155. Everyone can do that. I'm interested in these parts of questions which require manipulating the results and coming up with a conclusion. So you must have noticed, first of all, that the first value of theta is greater than the second value of theta, and the first volume we obtained was greater than the second volume, so that is fine. Then it is suggested that root of h is inversely proportional to cos theta. That is, root of h is inversely proportional to cos theta. That means the relationship we are talking about here, if I introduce a constant, bringing in a constant means a constant k is going to be equal to root of h times cos of theta. So there's a constant k is going to be root of h times cos of theta. Then they're asking us to explain whether the results of your experiment support this idea. So we are going to calculate values of k. Since we have taken results twice, we shall get two values of k. So k1 is going to be equal to the root of h. What was our first value of h? I think it was 8. Without wasting time, it was 8. So it will be root of 8 cos of the angle. The first angle was, I think it was 56. Yes, cos of 56. It is cos 56. Then our second value of k, we shall call it k2 for the second attempt, to be root of h. Our h was 5.2 cos theta. Our theta is 41. So let's press our calculator to see these values. Root of 8 times cos of 56, that is 1.58. 1.58. Then root of 5.2 times cos of 41, that is 1.72. So those are the k values. So explain whether the results of your experiment support this idea. So first of all, we are going to choose a criterion that we check against. As a teacher, I told you you have to encourage your students to choose a criterion to test against. And I told you that I normally tell my students to choose between 5%, 8%, 10%, 15%. That is the most, and even 12%. So a student will say, let my percentage acceptance range, let my percentage acceptance range of error in k values. Let my percentage acceptance range of error in k values be, maybe I will say 15%. So I'm going to check if the percentage difference in k values is less than 15%. So percentage difference in k values equals to, so we get the highest is 1.72 minus the lowest is 1.58. My students always prefer to divide by the highest, so divide by 1.72, then times 100. You can divide by the average, no problem. So this will be percentage. So I'll check with my calculator. 1.72 minus 1.58 divide by 1.72 times 100. So this gives me 8.1%. So this is 8.1%. Remember I said I was testing against 15%. Now my percentage difference is 8.1%. Then I now write my conclusion. I will now write my conclusion and say, since the percentage since the percentage difference in K values is less than 15%, then my K can be, or we can say root H cos theta is a constant. Root H cos theta can be considered a constant. Root H cos theta can be considered a constant. And if we can consider root H cos theta a constant, then the relationship is supported. Then the relationship is supported because we have seen that root H cos theta can be considered a constant since the percentage difference in K values is less than 15%, root H cos theta can be considered a constant, then the relationship is supported. So that is how we answer such a question. We choose a criterion, we test against it by calculating our percentage differences, then we give a conclusion. Okay. Then last question, state 4 sources of error in or limitations of this procedure. In this experiment, these are some of the limitations I expect. We have carried out the experiment just twice, so we have 2 readings. So you can simply say 2 readings. Two readings are not enough. Are not enough to draw a valid conclusion. Two readings are not enough to draw a valid conclusion. Of course, here you take more sets of readings and plot a graph. Take more sets of readings and plot a graph. You could take more sets of readings and plot a graph. Number 2, of course, when you're measuring the angle while holding your protractor in your hands, there's parallax error. When you're measuring the height h, when you're measuring this height h from the bench, there are 2 sources of error. There's an error because the ruler may not be starting, the zero of the ruler may not be at the bench. It may be starting from somewhere. Some rulers are, many of the rulers are, the zero is slightly above the bench. So it becomes hard to measure this height h when the bottle is on the bench. So there could be parallax error in measuring h, especially when you're holding the ruler. There is parallax error in measuring theta when you're holding the protractor in your hands. The hand cannot remain still. So this results into parallax error. So we can say parallax error in measuring h and theta. So parallax error in measuring h and theta. Parallax error in measuring h and theta. And of course, this is easy to solve. If you want to avoid the parallax error in measuring h, you just put a scale on the bottle. So put a scale on the bottle. Put a scale on the bottle, I think it is LE, to measure h. Instead of measuring with a ruler, to avoid parallax error, you could impress a scale on the bottle to measure h. Number 2, or alternatively, since I mentioned the theta, or every time you're reading the scale, to avoid parallax error, the eye level should be perpendicular to the scale. Eye level should be perpendicular. Should be perpendicular to the scale. The eye level should be perpendicular to the scale. Okay. Then next, of course, they told you to measure theta when it is just about to topple. It is hard to decide when it is just toppling, so it means that is a limitation. Judgment of or deciding on the toppling point is kind of going to vary every time. So difficulty in deciding. Difficult in deciding the toppling point. It is difficult to decide the toppling point. So how do we solve this? The best way to solve this is you can try it and see if it is better. You can hold the bottle with a Newton meter and tilt. When the Newton meter reads 0, then it means the bottle is just about to topple. So hold the bottle, with a Newton meter. With a Newton meter and tilt. And tilt until F equals to 0. Until the Newton meter shows 0, then it means it is just about to topple. So hold the bottle with a Newton meter and tilt until F equals to 0. Also, of course, you might have used a ruler that does not start at 0. I would just add these ones here. Let me first write the last one. It must have been difficult. Okay, let me write it here. Difficult to measure the height h owing to refraction, the shape of the bottle. So difficult. It is difficult to measure h owing to refraction or due to refraction. Owing to refraction. Shape. The shape of the bottle, it may not be perfectly flat. Shape of the bottle. Or you might also have noticed that the thickness of the bottom of the bottle is not taken. The thickness of the bottom of the bottle is not taken into consideration when you measure from the table. You're not consider when you want the height of the liquid in the bottle, but the bottle has a thickness at the bottom which you are not considering. So thickness of the bottom is not considered or not taken into account. Now all these relate to the same quantity, so you cannot say that there are different there are different limitations. They are relating to the same quantity H. So if you write in parts of these, which are where I'm putting stroke, you are writing the same quantity, you are referring to the same quantity. Or you could also have seen that the ruler does not start at 0. The ruler does not start at 0. The ruler does not start at 0. Or you could say difficult to line up the protractor. Difficult to line up to line up the protractor. So it is difficult to line up the protractor because the bottle is not because of the shape of the bottle. So all that could be referring to almost the same thing. And how would you solve that? Of course, I'll only look at the part where the bottle is where there is refraction, and I will say add a dye in the water. Add a dye in the water. Of course, that means refraction will not be very vibrant. Refraction will almost be not there. Add a dye in the water. And for the part of the limitation where the ruler does not start from 0, you could use a ruler with a 0 at the start. Use a ruler with a 0 at the start. You could use a ruler with a 0 at the start. Okay. So those are some of the limitations and the methods of improvement. Of course, there could also one that you could not have noticed by looking at when you look at your bottle. You could also notice that if you look at the bottle, it could be difficult again to measure theta because the container is not perfectly at right angled. So difficulty in measuring theta because owing to the container not perfectly right angled. Not perfectly right angled. Okay, so that is a limitation. Of course, this is easier to improve. We would even say the bottom it is not perfectly right angled at the bottom anyway, because we are measuring the angle at the bottom. So not perfectly right angled at the bottom. It was difficult measuring theta owing to the fact that the container is not perfectly right angled at the bottom. So this one would be solved by saying make the bottom square using plasticine. Make the bottom of the bottle square. You can just put plasticine and make a square at the bottom so that it's easy to measure the angle. Make the bottom square with plasticine. This method of improvement that I wrote in the last part of the question that add a dye, this could also solve the fact that the meniscus is not visible. I could also say difficult to measure H owing to refraction, or difficult to measure H because the meniscus is not clearly seen. You can say cannot see the meniscus clearly. Cannot see the meniscus clearly. You cannot see because the bottle is transparent and the water, it becomes hard because it's almost like the bottle could be of almost the same color as the water, so or may look almost the same as the water, so it may be difficult, or you may not easily see the meniscus, and that can be solved by adding a dye into the water. Okay, so these are just sample answers. They are really not the same answers for every practical. So you just use I'm just showing you how you write, how you present your work. That is all. It's not a guarantee that they will bring the same questions, the same practical, not at all. You just need to know how to present your work. So here I gave another limitation which could not fit in the space, the difficulty in measuring theta owing to the container not perfectly right angled at the bottom. And I said make the bottom square with the plasticine. And also there's a problem of holding the ruler in your hand, the protractor in your hands when you're measuring this angle theta. You could also just use a clamped protractor. Use a clamped protractor. You would use a clamped protractor. Okay, so thank you. I think that is enough. I've tried my level best to record this, and I want to stop here. See you again. Bye bye.